All right, welcome everybody, all of you. I should be taking notice, right? My class is too hard. It's too easy. So, what was the project everybody's working on? 370. So, what my takeaway from that is 370 is a more important class than 420. Oh yeah, that's what I think. All right, so any questions on anything? Yes?
Project. So we do for the project, it's a small signal model, not small signal model, short channel process.
Wait. For the project, you're using the C5 process, right? Okay.
It's a short channel.
Well, yeah, it's kind of short channel. It's not as bad as the 50 nanometer process.
So this is where, when it comes to doing my math for everything, sort of saying is, when I'm looking through the book on the small signal, I'm struggling to figure out how to divide. DC equations pulled up?
No, so when you do, that's why you need the sims from chapter 9 to try to pull like FT and the GM and all that, because you can get the KP. I mean, you could plot, for example, you could say, oh, here's my ID versus VGS for VDS equal to 2 volts, and you get a curve that looks like this, and you can read the VTO off the data sheet, it's 0.8, and then you could plug in for the specific size, you know, whatever current you read at whatever VGS, and you get ID equals KP over 2 times W over L, VGS minus V threshold. The only thing you don't know is this, right? And you can solve for that. But then when you change it, it's going, because the mobility is going to change, it's not going to give you really reasonable values. That's why we didn't solve for KP when we did the 50 nanometer device.
So for the report, is there a way, not even for the reports, is there for future, like for...
Use the plots. So you design with the plots.
Do we want to see, so last night, for example, I solved for all my GMs using DOS. I solved I had all the different, like 3 to 5,
okay.
all the different stuff. I did the same thing for the RLPs by using 1 over CPD.
Mm-hmm.
And then, so would we similarly want to do like a table with your KP values for...
No, I don't think you want to do KPs, because when you change the sizes or the VGS, and you solve the same exact equation with a different VGS or the different size, you're going to get a different value for KP.
Okay.
So I think that's an issue.
Right. So explain a few things on my end.
Yeah, well, I mean, this is real process. It's not the old 5 micron, 10 micron minimum channel length.
Right, so it makes sense not to have a standard KP.
Yeah.
Okay.
Yep. That's why I didn't do it in the book.
Right.
That's why I did all those sims in the end of chapter 9. Any other questions?
You started what was the minimum channel for some of the
The first doesn't, well, I mean,
it's a meter.
Actually, when I did my PhD, you know what the channel width was? I did power MOSFETs, and the effective width was meters. And it's because they put lots in parallel. So you'd have like a channel length of 0.8 microns and then a channel width of 3 meters. But you think about it and you go, wow, that's a lot. But it's really, if you take a piece of string that's 3 meters, a piece of thread, and you wind it up and it's really small, you can get 3 meters in. Easy. Especially if the width is 0.8 microns. Right? You just put them all in parallel. But the first MOS design I worked on was 4.5 micron minimum L, and it was NMOS only. So there were no depletion NMOS and no PMOS. So I said that, and I'm like, they don't know what that means. What kind of NMOS are we using from 421? An enhancement NMOS, meaning you have to apply a positive voltage to enhance the channel. What's a depletion NMOS? Normally on, it's a negative threshold voltage. The threshold voltage is like this. So you have to apply a negative gate to source voltage to shut it off. So this is depletion, and this is enhancement. Normally almost everything's enhancement nowadays, so they don't talk about those two terms. But in the older, like, has anybody ever heard of the 68,000 Motorola processor? It's one of the first big processors, like a lot of the Apples were made. They were, what's that? I want a documentary. God. The NMOS was, there was an enhancement and depletion, and so you'd make inverters like this. And this was the enhancement, and then this was the depletion, and this was the enhancement. So this was your out and your in. So.
I have a question.
Yes.
So, for my project, I was using PMOSs for current sources instead of doing the.
You mean a diff amp that's a PMOS diff pair?
Yes.
Yep.
And so at the last lecture, we were saying we could put the extra couple on the bottom.
Yep.
And shorten our lengths.
Yep.
And it would be the same. That way we don't have to have the resistor.
Yep.
So whenever I did that, my curve for my open loop gain completely flipped.
Wait, you're doing the following, right? You've got.
I mean, you put two extra PMOSs up top because.
Yeah, let's do it on a piece of paper.
The sync, but.
So we have the following. And it should work.
So before my curve was like this, and then whenever I did it like that, it flipped and it went like.
Well, that means that something's not biased up right. Or if you have high gain still, it means, well, let's ask this. If you have your plus and minus terminals switched, in one case you'll get a gain that looks like this, in the other case you get a gain that looks like this. So let's determine which is the positive and which is the minus terminal here.
Well, it would be opposite than what you've been doing with the
No.
I have my.
Let's see.
I have my positive side on the left
Here?
and my negative on the
This is what you're saying is positive?
Yes.
Let's find out.
And I have my feedback on
This is what you say is negative, so you got a big capacitor here, and then a resistor, big resistor here, and then you have this, so you're at whatever, we'll just put 2.5. Got to bias up the input to be in the common mode range of the diff amp, right? We spent a lot of time on that. Okay, so let's see if this goes up, what happens here? Wait, this shuts off. This is diode connected, so this goes down. If this goes down, this goes down. It's the same node, which shuts this off, causes this node to go up, and this node to go down. So is that the positive terminal? That's the negative terminal. No, it's supposed to go to the negative. Negative feedback.
But it's been working the whole time until, okay, so whenever I add those two at the bottom, then I need to switch it again?
No.
My design
You're doing something else wrong.
Been working perfectly until I tried to do that and eliminate my resistor and stuff.
I don't know. Oh, it's all right there. You're doing something simple. Just look and see what you're doing wrong. I mean, I don't know if you send me a schematic, but I can't just sit here and go, well, I don't know what more to say here, right? What, seriously, what can I do? Just doing something wrong, it's pretty straightforward. If you say this is the plus terminal and it had been working, then there's some weird state it got into where it's biasing upright, and when you change something minor, because of that plus and minus inversion, it stopped being biasing upright. Even positive feedback can be stable at times, right? I mean, an example of that is what? Yeah, BMR. Yeah. Yeah, because we killed the gain with the resistor. All right, and then if you tweak something like we add the capacitor, it can cause it to be unstable, even though everything else is the same and working perfect. So I don't know what to say. All right, let's talk about any other questions? Yes.
I think I have trouble doing biases. I think we already I talked about the KP, how to the transit. Actually, I try to make sorry the length, the weight. The KP I think depend on the transistor.
Yeah, it varies. You can't calculate that, as we discussed in the,
yes.
yeah, we discussed this at the beginning. You can't get a value for KP because it changes based upon the size of EGS and the VDS.
Yeah, I already got how to get GM and how to get
Yeah.
W and L.
Just like we did in the end of chapter 9.
Problem is VTH, because I'm trying to calculate VTH. Is the PMOS is a negative 0.9 something.
Yeah, remember most people, okay, so you get the VTH by looking at the plots. You get everything by looking at the plots. We're not doing anything different than what's in the book for the short channel process. You're now, if you think long channel process, we're saying here's some long channel parameters, and the whole point of those is so we can do hand calculations without just reading values off the charts. Okay? So when you ask what's VT0, you can get a good approximation looking at the model, because there's a VTO, right?
Yeah, it's a negative. PMOS.
But if you want to see what it actually is, you do the plots. When you go work in industry and they say, here's your models, they also give you a design manual with all the plots already in it from measured data. They take those measured data plots, and that's how they generate the SPICE model. So you design from the plots.
Okay, that's the problem I see.
So when you say, what's the threshold, I'm like, why are you asking me? What's the simulation say? And if you ask how to simulate, I'm going to be like, good grief, how many times have I done that in the book? I mean, to give you examples on how, I mean, it's in the end of chapter 9. Here's how you get GM, here's how you get R out, here's how you get FT. All those things, we're not doing anything different than what we've been doing. You can't calculate a VTHN for every single situation because it's going to vary depending on the size. Same thing with KP. This equation is only valid for old technology. Old stuff. That's why there's 2 processes in the book instead of 1. It wasn't like, hey, I'm going to write a book, and you know what? Just to make it extra hard on myself, I'm going to write it with 2 processes for examples. I did it so, and it's in the preface, I did it so that you can write, you can do the hand calculations using parameters that don't vary like you do in 320. Or then I did the nanometer process so you could do it like it's in the industry. You know, what's going on in industry. I get a manual, I have to do everything from charts because I can't use these old square law equations. We went over that though, lots of times. I hope it's better than that one.
Okay, you said specifically in, you said VDD in 10 microns, no driving more than 10 milliamps, yeah. What's that supposed to
That's the
mean?
power supply current. VDD is your power supply.
So we get from there 10 micro, we have
10
to
milli.
How are we going to do it? We have to make.
Here's my op amp. This is the circuit I'm designing, right?
Yeah.
Connected to it is a ground and power. The maximum current that I can supply there is 10 milliamps. That's all it means. So let me ask you this. If my output goes to 4 volts and I'm driving a 1K resistor, how much current am I burning, or is the op amp supplying just to drive 4 volts into the 1K resistor? 4 milliamps. So if I would have said, hey, you can only have 1 milliamp of op amp current, but you got to drive 4 volts into 1K, you would have said, hey, that's ridiculous because my op amp needs to pull more than 4 milliamps just to drive that load. So what's the maximum power dissipation? 10 milliamps times VDD. If I ask, okay, if it's pulling that and I get 4 milliamps, if this is 5 volts, that's 4 volts, what's the percentage power dissipated by the op amp? What's the percentage power dissipated by the resistive load? This is 40%, this is 60%, because I know 6 milliamps will go in here, 4 milliamps will go in here, right?
And last question, if you don't mind.
No, these questions are killing me. All right, lay it on me.
I think I have a problem with the zero and the pole. I already figured out how to get the pole
Uh-huh.
each node, but the zero is make me hard time to figure it out.
What do you mean, figure it out? Do you have a zero and you want to get rid of it?
Yeah, because we need to understand for the pole.
Why don't you do this?
Which one?
That
Yeah,
gets rid of the zero. And if you say you have a zero, it's not biased upright. What's that?
If I have any more, I'll come to your office.
Bring a schematic, because you show me something and I'm looking.
I already started and write it.
No, I mean what you're simulating, because if you...
That's good, but there is issue. I have over down, which is at my degree I think less than 60 degrees. That's why it has to be moved. That's the things I'm trying to figure out.
So how do you reduce or increase the phase margin?
I have to use the pole. I have to put inside.
No, you're talking really deep. I'm asking you, how do you increase the phase margin? Just tell me real simple. Oh, my phase margin's only 60 degrees. What do I do?
I think increase CC.
Yeah, increase CC,
yeah.
or I can increase the transconductance, and it'll put the push the pole out if I want to do that. If I reduce the transconductance. But let's ask that just to make sure everybody follows. Let's say that I have the following. So this is F unity, and I say it's equal to F2. This frequency is what? Which is also F1. What is F1 called? What is that associated with? The pole on the output of the diff amp, or the input of the second stage. What is F2? The pole associated with the output of the op amp. We know F unity is equal to GM over 2 pi C sub C, right? So now, if I look at this and I ask, what's the phase shift? And let's do that in brown. At low frequencies, let's just say that's 0. The phase shift is 0. However, 1 decade above the 3 dB frequency, which 1 decade means 10, we start to roll off. So we start rolling off, and at the 3 dB frequency, we go over and it's minus 45 degrees. Then at F1 times 10, or F3 dB times 10, we're at a phase shift of minus 90 degrees. This is due to F1. Does everybody follow that? Okay, but that's not the only phase shift we have, right? The other phase shift we have is due to F2. So at F2, we go 1 decade below, and let's say that's right here. And there, we're at 0 degrees, and then we start rolling off, so that at F2, we're at 45 degrees. And then we go to 90, which is 10F2. We're at 90. Does everybody agree? So if these are far enough apart, I add these two together. So this would be, looks like 90, but it's supposed to be 45. I get a phase shift overall. Let's see if I can write it out. of minus 135. Does everybody follow that? And you say, let's ask several questions. How do I, without changing the unity gain frequency, improve, which means without changing the transconductance, oh, so this GM is the transconductance of what? Diff pair. I can't change that or C sub C, or else I change the unity gain frequency. So if I want to increase the phase margin, what do I do? Just looking at this and talking about F1, F unity, F2. If I want to increase the phase margin, what do I do? Don't think deep, just look at the plots. I have to move either F1 or F2 because I just told you we're not moving the unity gain frequency. I got to move F2. I had to move F2 up.
But I thought M2 is.
No, I just said, say they're at the same frequency.
Oh, okay.
Okay? So I need to move F2, I need to move this way so that instead of having this, I have the following. So now this is the F2. It's moved up. Does everybody follow that? So I need to move F2 up because then if I do, the phase response from F2 is going to be further out. Why don't we pause and I'll show you what I'm talking. And you ask, well, before I do that, how do I move F2? What's that? No. Let's look at the equations from chapter 21. Let's see what determines F2. So F2 is GM2 times CC divided by CC, C1, C1, C2, C2, CC. So I can't move CC, right? Can't move C1 and C2. Those are the capacitances of the transistors. The only thing I can move in here is what? GM2. So if I increase GM2, what happens to F2? It goes up. Does everybody see that? So let's go back and look at a figure. Does that make sense? Okay, so let's go back and let's look at figure 2419. And I look at this and I go, okay, well, I'm using the indirect compensation here. And what did I do? Why did I add? Oh, this is an indirect comp. This is a different topology. Let's look at, nope. Oh, here we go. All right, so this is what we kind of left off with last time, right? Does everybody recall? And the whole point of this was to get rid of the zero. So I hit run. And I look and I say, cringe, where is the unity gain frequency here roughly? Close to 200, right? 180 or so. Does everybody see that? Right here. That's the unity gain frequency. Where is F2? Right here, right? About 400, 420, something like that. We'll just say 400. Does everybody see? Okay. Notice if I go up to F2, phase shift is 135 degrees. Of course it is. We got the 90-degree phase shift from this low frequency pole, and F2 it adds another 45 degrees, so we get a total phase shift of 135. That makes sense to everyone. So now I just said, hey, I can have better stability. Here the stability is okay because the phase shift is about 90, but say it's 100, let's say it's, we want to push this out so it's flat even longer. How do I move that F2 out to make it more stable? Yeah, increase GM2. How do I increase GM2 here? Because remember, I don't want to start fiddling with changing my overdrive voltage. All I want to do is increase GM2. Well, what is GM2? It's equal to square root of beta times ID. ID, what's that? 2 beta ID, yep. So how do I increase that? Well, let's look at the other equation. It's beta times VGS minus V threshold N. VGS is overdrive. I'm not messing with that.
You could split it so that beta W over L, so instead of L being
Well, I don't want to mess with L either because then that changes FT. All I want to do is increase the W, which increases the current. So I want more current to burn in the output stage. So let's see what happens. Let's make this, heck, let's go 9, and let's go 8. Why not? And so what am I doing? I'm increasing the current that flows in this stage. The overdrives stay the same. The FTs stay the same because FT is not dependent on the width, right? I burn more current, that pushes GM2 out. So if I look at the response, what I'm going to see is I'm going to see this move out and I'm going to see this stay flatter longer, making my device more stable. So I hit run, boom. And it only moved out to, well, nothing super significant. It moved out a little bit, but you get the picture. If my F2 was down here lower, it would be more pronounced because you'd see it rolling off. So why don't I do that real quick, just for the heck of it? Yeah. Let's go, let's see what this one is. Transient. Let's do it a different way. Let's look, see how that's messed up? So let's see what happens. It has the 0, but let's see what happens if we move F2 out further. So let's do the same thing here. Let's say that's 8. I don't know if it'll do anything because of the 0, but we'll find out. Hey, I moved F2 out. That 0 is even still there, but now that F2's moved out, it's more stable. Let's see what happens in the phase response. Does everybody follow what I'm doing? Okay, so let's go look at the phase shift. And it's the same thing. And my F2 is right here. Okay, there's my 0, so that's not good, but my F2's over here, so let's see what happens if we push it out.
So all of these changing the width and stuff, you can do it on your second stage, right?
Well, no, you can change the width of your diff pair a modest amount because that'll increase the GM. So if you want to push your unity gain frequency out a little bit, you can do that. Is everybody cool with this? So let's see what happens. Notice how the pole moved out, moves the 0, 2, but notice how it's more stable now. But of course, what am I giving up? No, the gain stays the same. My battery's going to drain faster. My unity gain frequency is not changing. If I go back, here it's 10 megahertz. Gain is whatever, 60. And I go back now and I rerun. Gain is the same. Unity gain frequency, that 0 If it wasn't there, it would still be coming down, but the unity gain frequency doesn't change much. Does that answer your question, Warku? Okay. So now, if I go back and I ask what I just said about the comment, about changing the widths, if I look, the only other place you would want to change your width, I mean, other than when you do the initial design, you select a width, right, so that you get your slew rate limitation, so you know how much current charges your compensation capacitor, is in the diff pair. If I go in the diff pair and I make these W's, say, 4 times the W, they're not setting the currents because there's a current mirror that biases them, right? But if I increase the width by a modest amount, then I can get a larger GM, and then my unity gain frequency, which is the GM of the diff pair over 2 pi C sub C, can go up a little bit. Now, why don't I increase the width a lot? Well, what happens is you can tolerate a modest amount in increase in width because it lowers the FT of the transistors. But if you say I'm going to go 100 or 40 where the gate source voltage is close to the threshold voltage, well, now they're really inherently slow, and their FT, that pole they introduce, comes into play with the op amps that we have. You know, when you select your FT, you want to have your FT so it's at least 10 times bigger than your unity gain frequency, so then when you put your circuits together, they're not interfering. The transistor's inherent speed doesn't interfere with all these equations, all right? So I would start out and I'd say, oh, well, I got made 100 megahertz, so I'm going to make my FTs at least 1 gigahertz. And then you could say, okay, well, what if I use the same overdrive, or I use a larger W, what happens to the FT? Well, okay, if I look at same biasing, nothing. If I look at a reduction in current, which means a reduction in VGS, they're going to get inherently slower. Would it be helpful if I talk slower?
Sometimes. So adjusting for like our push-pull buffer thing on the...
You need to boost but remember in that one, it's not the 4 transistors that are the source follower, it's the 4 before it that are the GM, because those are the gain stage. But you would need to increase the sizes of the 4 on the output to match what you increase the previous ones at. So let me show you what I'm talking about, just to make sure I'm not doing a wah again.
But the increasing the width, like doing my n times whatever, it's like it's not going to affect my that particular stage, that buffer isn't going to affect the gain.
No,
All
this
that's
has
gonna
got a
affect
gain
is
of
my
1.
Push and pull of my...
Yeah, this is a gain of 1, all right? But this, the gain from here to, these are essentially diode connected, so AC-wise these are the same voltage. The gain from here to here or here is going to be exactly what we had with our op amp, right? Because all we're doing is we're cutting where the op amp we were just looking at and using these transistors here. You know, let me just pause for one more minute before we talk about the others and go back and do that for this circuit. Because I'm sitting here and, here, let's go back and do it for the more split length ones, which was it this one? Nope. This one. Now, nope. Nope. Yeah. So keep in mind, I don't know if that buffer will meet the specs and your requirements. I don't know, I don't remember what I said. It may not work because it's really limited output swing because you got the NMOS on the top and the PMOS on the bottom. But let's do it, see what happens here, all right, if I add the buffer to this schematic. Or actually, you know what, let's run the sim first. Looking good. Then let's get the scissors out. And then let's go, hey, let's move this to here. And then let's copy. And we'll do a copy like this. And let's stretch this dude. And then let's copy the NMOS, and let's just copy this one. And get rid of that. Every time I do this, I just think how nice PowerPoint would be. Looking good. And if you wanted, we could stretch this a little bit. Whatever. All right. And then let's move this out of the way. What's that? Oh, okay. Let's move this out of the way for now. And let's put a wire in here. Now I could actually connect it to this node, but I'm not going to do that because the output buffer has got a gain of 1. I'm going to connect it to the output buffer. And I really don't like this because if you turn in schematics, I want them to be pretty. So we'll do this. Not, looks like you threw a bunch of transistors at a canvas and you're, yeah, it's art. Alright, and then we go over here. And then we go, oh, well, we can connect this here. Whoops. I get the scissors out. And then let's go boom. Boom. Copy. Oh, I didn't do the top one either, did I? You're probably going crazy on that, aren't you? There. And then move this. Does everybody see what I'm doing here? And last but not least, CC. Oh, see what you have done. Probably nobody got that reference. Elvis. CC Rider. Okay. Let's hit run. Oops, I don't have something biased up right. Let's see what I did wrong. That's right.
Yeah, but my second stage
You did something wrong then. Oh, what did I have wrong? Gotta go to the op-amp output, don't I? Now let's try it. Still not right. Okay, V out, V bias 3, CC.
You have two capacitors, just
I have what?
two capacitors, 10P and 10 over there.
10P.
Yeah, that's the one.
Where is it?
Very,
Here?
that one and also another one.
This is
Connected
the
by
load.
EN.
What's that?
You connected it here and board.
This one?
That one.
That's for DC stability. That's the same. Got something easy here. Let's just see what it is. Like the V out's not connected right. Let's see. All right, all you guys look at it and let me know what the issue is. Let's do a .op and find out. Run. So this is 0.5 volts. Oh wait, something's wrong here. 150, 100, oh. Does everybody see the issue? So when I copied, my L was 100, but when I split these up, I use 50s. So here I have a 50, here I have a 50, and I need hundreds. But wait, the way I have this, it still should work like that. That's 50. Oh, that's an issue. 50. Oh no, that's right. 100. 5, 2.5 is 100, 2.5. This should be 100 and 5. This should be 100, 2.5. This should be 1. It still should have worked. Something else isn't right. Let's see. Run. So this voltage is 0.5. This one is 496. That seems reasonable. This one is 960. That seems right. 619. All right, let's go back and do AC again. Run. Something else isn't right. You guys get to see me feel pain. It's good, isn't it?
I have a question.
Well, if it helps me solve what the minor issue is here, I'm not seeing what it is. Let's see. It's 150. Let's see. I guess with the AC I do a dot. So that's 516. That's
CLC connected outside.
this is the load. That's the DC stability. That's the compensation capacitor. What's that?
Should those gates be connected? On
Which gate?
M23B and or M3B and M3T on the top left of the top left. Should they be connected?
Yeah. What I'm worried about is I didn't do any calculations on the minimum voltage here, and I'm thinking it may not be. That's one of the issues with this is with the body effect and the transistors, the VTs go up, so I may not have enough power supply voltage with this low voltage. That won't be a problem. Yeah, that's the issue. That won't be a problem in your process because you have a 5-volt VDD, but here it is because the body effect of this one and this one are bad. So here, let me show you. So if I don't have body effect, so I don't have enough high voltage to drop across these, but if I get rid of the body effect, so if I do this, so these are no body effect in those. Does everybody follow? When I say that, what does body effect do? Yeah, it increases the thresholds. When I put two devices right in the middle stacked that have a high threshold voltage, they can make the minimum power supply voltage be above what it is in these nanometer process. That's why this topology isn't used much. That's why I want to talk about the other topology today. So you see the gain go up.
Widths on two a little bit different on the part you added there. The one is 5U.
Yeah, that's the PMOS.
The one above it is 2.5U.
That's the NMOS.
Oh, okay, so I didn't catch
That's the PMOS, that's the NMOS. So you see there's some issues with the DC biasing. Why don't we pause here and talk about a more practical for the nanometer CMOS output buffer? Is everybody cool with that? Okay. So let's go do that. Actually, that makes me wonder. Okay. So everybody understands that the topology we just looked at is limited because the output has this structure. So this goes all the way to VDD, which we know it can't for everything to stay in saturation. Then the output goes where? Can go up to at most what? And this has body effect, so the VGS is even going to be larger. And this one has body effect too, right, Rudy? So it can go all the way down to V threshold P with body effect, which could be well above, or I'm sorry, VSG, which could be well above what I have with no body effect. So the output swing's really limited. So we don't like that NMOS on the top and PMOS on the bottom, so let's consider what happens if we do the following. Okay, well, if you do this, you can't use the biasing circuit we just talked about with the two transistors in the middle because the gate sources.
I didn't have the transistors. I didn't add those transistors in the middle.
Well, how do you bias this so that it biases upright?
It's connected to my
It don't work.
V bias that's coming all the way across from my DMR.
Well, okay, wait, maybe, are you talking about this as being the output of the two-stage op-amp that we discussed right at the beginning of lecture where it can't drive resistive loads?
That's my buffer.
Wait,
I've got the second stage. I've got my op amp, my second stage, and then.
yeah, but if you have 3 gain stages, it don't work. It's not going to bias up because you got invert, invert, invert. Well, now your plus and minus are switched and you have a 3-stage which requires 2 compensation capacitors to keep it stable, and it'll never bias up correctly. All right, so let's look here. Here's my output, and I need to set this voltage, correct? So I'm going to do what? I'm going to put what's called, well, first off, let me ask this. If I want to just, let's assume I put these together. We won't worry about how we bias, but let's assume both are operating in saturation. So we can put batteries here, whatever. But let's just calculate the gain, V in to V out over V in. So what is the AC voltage? Here's V in. So what is the voltage here? Does everybody agree? What's the current that flows through my 2 resistances, R out N in parallel with R out P? GMN times V in. But wait a sec, I've got V in here, which is equal to minus VSG. So if I ask what's the current that flows through here, you say it's GMP times VSG, which equals GMP times minus V in. Or I got a current going up of GMP times V in. So V out is equal to R out N in parallel with R out P times GMN times V in plus, also going out, GMP times V in. So V out over V in is equal to R out N in parallel with R out P times GMN plus GMP.
Should there be a negative sign since the current's coming out?
So the current flows down like this in the PMOS, and it's GMP times VSG,
Yep.
but VSG is minus VN. So I flip it around, just like this current, it's leaving the node in the same direction, GMP VN, and so I add the 2 together. Does everybody agree with that?
There's no minus sign?
I already had the minus sign in here. I flipped the current around so it was going in the same direction as the NMOS. Okay, so you understand this voltage plus minus is Vn. This is AC ground. So this voltage, VSG, which is defined as from plus to minus like this, is minus Vn.
Right. It's just that the current isn't coming up from ground through the R out N in parallel.
Oh, sorry, yes.
Okay.
I thought you were talking about this up here.
Right.
All right. Yep, keep me honest. Does everybody see? This is called a push-pull amplifier. And it's really useful because what can the output swing up to? And then down to? So almost rail to rail. If I have 100 millivolts like you may design for in your projects, you can get to 4.9 volts down to 100 millivolts, really wide swing. Also, it's class AB. So what that means is if this goes up, this shuts off, this turns on, and all the current can be discharged this way. And if this goes down, now keep in mind they're going together, this guy turns on, off, and this one turns on, and get good pull up. Okay, so I'm going to go through now. This is a push-pull. Now, unlike the topology we just looked at where the source followers have a gain of 1, this doesn't have a gain of 1. It has a high gain, right? So I need to make sure when I design this, I incorporate the, this is the second stage of the op-amp. Is everybody cool with that? Okay, so I'm going to do the DC biasing first. Before I do, any questions? Stop filling my head with information. Okay, so here's how we're going to do this. I'm going to go through the stages. What do I want this to be here? And what do I want this to be here for DC biasing? King of trivial questions. That's what we want. We want it to bias up. We have to set those voltages, right? So now, the way I'm going to do that is the following. I'm going to add a transistor here where I have plus minus VSG. So here, in my bias stick, which you've seen in chapter 20, and this will be called VPCAS. So what does this do? Pulls a constant current through two diode connected transistors to give me two, what is the voltage here? Does everybody agree with that? Any questions? Where does this reside? Bias circuit. Okay, then I'm going to come over here and I'm going to connect this to a, which I'm going to call that 2VGS or VNCAS, and I'm going to connect that up to a PMOS. So I get a VGS here and a VGS there. Okay, but there's no current flowing in those, so how do I get them to bias up correctly? The answer is the following. I'm going to put a PMOS here. I'm going to put an NMOS here. What do I label this? Then I'm going to do the following. So the current that flows in there is I bias. Current that flows in there is I bias. However, Rudy, what is the current that flows in each of these? I don't want to be a boring lecture. You know how a lot of your professors, at least for me, when I went to school, they were kind of boring. It's hard to stay awake. I don't want to be one of those people. What's that? Oh, and what would this current be? But that's not what I want. I want them to have the VGS. So I'm going to divide their widths by 2 or multiply their lengths times 2. So I'm going to make this a W over L and a W over 2. So if this was a 100 width, I would change it to 50. If this was a 25, I would change it to 12.5. So that the VSGs stay the same, VSGSs stay the same. Now everything's biased up, and this will go to I bias. What do I label this node? Just, yeah, V out. The output of the op amp.
Can you explain the I bias and I bias over 2?
So these, just a normal transistor. These two I half the sizes. So half the current flows in them, and this is a normal size transistor, so I bias flows in that.
How do you know that half the sizes have half the current flowing through it? Do those
How do I know?
Yeah.
If I change the width by a factor of 2, the current drops by 2. Yeah. Questions? Why don't we modify our basic op amp using this topology? Sound like a idea? Does anybody, and what was this topology called? Class AB or push-pull. And what's the benefit? Wide output swing. I hate to do what I'm going to do and do the problem because then everybody will copy me and will be like, you can do better than this. Yay or nay? Alright. I'll do it anyway because I'm a nice guy. Just ask me. Yeah, I think that's funny. You wouldn't believe how, oh, yeah. Anyway. Any questions? I got a question. If this node goes up, what happens to this transistor? Yeah, if I yank the source of this up, I turn the PMOS on, right? Wait, if I yank the drain up on this guy, not much happens. But if I yank the source up on this one, more current starts flowing through there. But the current that flows down there is constant. So that means this is going to go up the same amount, and that's going to turn off. So that the current stays constant. So whatever signal here appears will also appear here. So if this node were to go down, that would shut this off. This node would then go down and turn this one on to keep the currents constant. In fact, if I wanted to for AC, I could put a capacitor across here because the voltage between here and here is always going to be, I mean, within reason, without the power supply wiggling a lot, it's always going to be constant. Now, when on the final exam, if I see everybody in the class use this topology, which I'm guessing they will, then I will ask questions about this that are simple things to see if you actually know what's going on. Like, what happens if I increase the voltage on node 1 here, and I'll label this node 1, to the current that flows here? What happens to the current in this transistor and why? I can ask real simple questions like that and see who knows what they're doing in the project and who did monkey see, monkey do. Okay? So let's go do this. That's the whole premise of Curious George. Hope everybody knows that reference. That's from the 30s, right? Holy crap, pretty soon that's going to be a difference. When you say from the 30s, they're going to be like, I'm thinking 1930s. Pretty soon it'll be like 2030. Okay. Well, the way years are ticking by. Okay. They're not ticking by. I know, holy crap. I turned 36 in 2000, and I was like, the prior years, I was like, that's way in the future. 2000's way in the future, and now it's like, holy crap, that was 16 years ago. All right, so let's go modify this structure. So, tell me what to do. Get the scissors out. Yay or nay? What is this VPCAS? Let's find out. VPCAS, diode connected transistor, diode connected transistor. VNCAS, where's VNCAS? Diode connected transistor, diode connected transistor. These just make sure that the VDSs are more matched. But I'm going to know all of that when I use my project. Now what? Let's add those transistors in, right? And then let's get the stretchy hand here and stretch this up so I have plenty of room. Now what? Make sure I don't make, since past performance is the best indication of future performance, make sure I don't make the same mistake. Yep, so I'll copy in this one. I'm going to relabel this VNCAS. Looking good? Then let's go, and I got to remember to change this to 100. Oh, you know what? Let's, why don't we do it this way? And then this one is 100 and 2.5. And then let's go with a little bit of movage, because clean schematics are nice. And let's do a little bit of copying, except I need to change the label. What do I change the label to? Promise me when my projects are due that you'll skip some of your classes and tell the professors that you're working on my project. All right. Any questions? So now let's go copy. Do you think we're going to have the issues with the body effect on this one?
Yes.
I think it'll be okay. We shall find out. Why do I think it'll be okay? Notice we don't have these in series, they're in parallel, whereas before they were in series. But hey, when I'm wrong, you can say, wrong! Revoke your PhD! What does PhD stand for? Doctor of Philosophy. Did you know that? You did? It's funny because people go into my office and they say, I didn't know you had a doctorate in philosophy. And I'm like, that's what PhD is. And then, you know what, I better not make the same mistake as last time. Boom. And then let's go move this. And let me pause for a moment. Let's put this back up at 5. Or else we'll have an offset, and put this back at 2.5. Okay, so if Oh crap, you know what? This isn't going to work, and I'll indicate why before we move on. So does everybody see this is a high impedance node? It's a high impedance node. It's only connected to gates and drains, and I can calculate the gain as GMN of the diff pair times R out P in parallel with R out N. Everybody see that? This is a high impedance node here. I mean, these two are basically shorted together, but I have another gain there, and then I have another gain to right here. So it's a three-stage op-amp. But I'm going to fix it. What I'm going to do is I'm going to make it so that these transistors here and these transistors here are effectively 2 times the width. Does everybody see that? Oops, I need one more. Does everybody follow? Okay, so these are the same transistor. I could just put it as M equal 2. Whoops, I need one more thing. Crap. I keep saying that, and then I look and I'm like, no, they're not. No one's going to turn in this topology, right? Okay. So does everybody see source tied together in both of these? Gates tied together, drains tied together. Source tied together, gates tied together, drains tied together. Does everybody see that I have a gain from here to this node? And then I have a gain from this node to here. So this is my second stage gain. So if I want to increase F2, what do I do? So you'll need to know this. Increase the widths of these. Now, when you have a 1K load to ground, this guy's going to be supplying more current, so you may want to play with the width of this one independent of all these others, because it's always going to be if it's always driving a resistor to ground, it's always going to source more current than this one will, which is connected to ground. Okay, and if it doesn't make sense, let me go ahead and say File, Save As, just so we have it in case you want me to do something there next time. If that doesn't make sense, we can discuss it after you play around. But the only other thing I have left to do is what? Well, I guess I have 2 things left to do. I did. This was W's now 2.5 of the PMOS and 1.25 of the NMOS. Oops. Keep me honest, man. Okay, so let's move this over. Looking good? Let's see what happens. Run. Nothing will pop up because I changed the name. Plot V out. The gain isn't that high. Let's make sure everything's biased up properly. 500 millivolts. 500 millivolts. 644. Is that right? Do I want the gate here to be 644? I want it to be a VSG. VSG is 350. So this voltage would be 1 minus 350. Is 644 reasonable? Yeah. What about this voltage before I put my cursor on it? Want it to be 350. So let's see what it is. 352. Is everything biasing upright? Don't know. Let's see. These are 100 by 5s. Let's see how much current's flowing in those. 20 microamps. Let's see how much current's flowing in these. 10, 10, 10. Come on. 10. Now, I'll tell you what. If I was doing the design, these are going to need to be beefed up. Okay? So if I look at the response, I can see what my phase margin is. It's not that good. It's only 60 degrees. So I'm going to go fix that because I know how to do it. I'm going to make this 8.
We will have to use that terminology in our report. I had to beat it up.
I don't know. Let's see what happens. So now our Phase margin's about 70, no, 80 degrees. Does everybody see that? Let's see what happens when, so how would I increase the gain further? Could adjust the GM of these a little bit. Remember I said we can do that? These a minor amount because they control both the unity gain frequency and the open circuit gain, etc. Let's go ahead and put this in a follower configuration. Okay, so if I ask on this, what is the output swing using this topology can go very close to VDD and ground. Does everybody see that? But the input diff amp can't, can it? Does everybody see? It can only go to a VGS plus a VDS sat and then basically up to VDD minus a VDS VSD. It's just the input common mode range of the diff amp. That's limiting my output swing. Does that follow, everybody? So when you design your circuits, if you use this topology, you're probably going to be limited by the diff amp as your output swing, because the diff amp has to stay on as the output swing is swinging. So let's put it in a, let's hit save, save. Let's go back now and put it in a, where was it? Let's go to version 2 and we'll do a transient real quick. And let's get real quick, get rid of these. And let's change this to a pulse. And we can't go any lower than say 500, so let's start at 500 milli. Let's go to 600 milli. Let's have a delay of a let's do 300 nano, rise time 1 nano, fall time 1 nano, on time 100 nano. Hit OK. Change the simulation to a transient for, how about 500 nano? Hit OK. I think that's enough time to let the bias circuit start up. Hit run. Plot the input. VN is 500 to 600. Let me just look at a bias voltage real quick. Yep, looks like it started up. Then what do I look at next? The output. Boom. That's not that interesting. Let's beef up the capacitive load. Let's make it 1,000 pico or 1,000 femto. 1 pico, just factor 10. Let's get a little bit of ringing. Okay, that indicate that our phase margin's becoming marginal. Then I go up to and I say, hey, but I need to drive a load. So let's go ahead and put a load in. See if this bad boy can drive a load. Let's put a 1K in, just a pretty heavy load. I don't know if this device is big enough. Let's see what happens. It's marginal. That PMOS is having problems pushing it around. Of course, I did nothing. I just guessed. Let me see what happens if I go to 10K. Run. Oh, that's a little bit better. Any questions? Do you feel like totally lost for this weekend? What? Come on. I don't know how much more I can do other than sitting down and doing it for you. Doesn't this look cool? You can get your project and you can say, hey, this I'm going to put it on a t-shirt and make art, and people can say, what is that? And you can say, I know and you don't. Ha ha ha. Have a good day.